Okay, thank you. Please do wave if I get too quiet. My voice is going a bit, and I'm usually accused by students of talking too quietly, so you've been warned, but you can also feel free to come as far down as you can see, as long as your necks can cope. Okay, so I want to talk about the FocusedCasual Continuum in interaction design, and this is relating to many people feeling we're becoming increasingly distracted by these mobile devices that the Finns used to sell so well to the world. Everybody is continuously connected. We're able to access all the information of the world every minute of the day, and we're seeing some problems with that. So I'll discuss that, then I'll look at a proposal for having different ways at different levels of engaging with systems, and look at how people are using machine learning and new sensing mechanisms to have around device interaction, and talk about some specifics about looking at how you would measure channel capacity with a given sensor system at a given level of interaction, and how you can adapt your interaction to different specific locations. So let's start looking at how we close interaction loops with people and with devices around us. So here's a video that's been doing the rounds on YouTube recently. You may have seen it.
Driving with a box stuck under his car. And like, who knows how long he was driving. I saw him pull out of the parking lot and turn right, and the box was still stuck under his car. So who knows how long he was driving with that box under his car. I bet he got home, he pulled into his driveway.
Cloud in the sky. I'm not. Wow. And like, if you, it's not.
I don't think it's real. I don't think it's real.
I see the lineup for car. Getting wasted. The Empire State Building is like really close to it, so it's a good.
Okay, hands up if you can relate to anything you saw in that video. Okay, fine. This is a slightly extreme presentation of it. Sorry, I promise not to walk about too much. But you could see lots of examples in that video of people failing to close loops with the people who were important with them around the world. So people starting off socially engaging, but very rapidly becoming caught up in their mobile device, getting going with something on that, and then dedicating all their attention to that, you know. And you see, I'm sure you've seen many people wandering around with prams, ignoring their child, you know, busily entering something on their phone. You've all gone to conferences where everybody opens up their laptop. They've just traveled to Japan to hear the speaker speak, and they end up doing the most boring emails you could imagine, sorting problems back in the department, and realizing at the end of the talk, oh God, I just flown several thousand miles to be here and I forgot to listen. So one of the challenges is to think about how we can be more mindful about the way we interact with computers. So if we think about attention as a limited resource, we can easily get it immersed in personal private devices, displays, and that makes it easy to ignore people and events going on around us. We can get fully immersed, and we're compromising our physical ability to deal with things. You see people walking into lampposts, tripping over fences, crossing roads while checking their mail. You're also affecting your social life, your family's life, your mental well-being. We're seeing people having more sleeping problems because they're staring at bright screens just before they go to sleep, affecting their melatonin levels. So we continue to engage with our devices, often when we don't really need to. I mean, how often have you got into that cycle of sitting, you're tired, you're home, you quickly check your mail, it takes longer than you thought, you check your Facebook, you check the news, then you're back to checking your Facebook, then you check your Twitter. Before you know it, a few hours have gone, and do you feel particularly good at the end of that? Not always. So you could argue that when you're not really consciously deciding what you're doing and why, then your actions are becoming mindless to an extent. And one of the things that we've been thinking about is this notion of empowerment. So there's a technical definition of empowerment, which is the channel capacity from your actuators to your inputs. So how much information can you put out into the world and see a response back at your sensors? And it's interesting to see, okay, with a particular interactive system, you might have some rich input sensors and you get lots of feedback and you can do lots of control there. But by paying attention to that particular loop, what have you been ignoring? What have you been missing in the environment around you, from your family, from your friends? So we want to make conscious choices about where you're directing your attention. You should be able to choose how much or little you want to engage with technologies, your surroundings or other people. So sometimes the whole point of having your phone out is to scare off other people. If you're in the crowded London Underground and you've got somebody's bum in your face, you know, you're wanting anything to make you pretend that you're not there. If you're sitting in a bar and you don't want people to come up and talk to you, then pulling out a phone or a tablet is a good way of creating a distance. So sometimes you want that, but you should be in control of that. So you want to look beyond these immersive experiences and think about how you can engage with devices more mindfully. So when people are designing for mobile devices and designing the devices themselves, they're often implicitly assuming the user is going to be fully engaged all of the time. But that's not always possible or appropriate. So if you look at some of these scenarios, you've got somebody carrying shopping bags, dealing with a windy day, generally physically constrained. That's going to limit how they can interact with the device. You've got somebody here, tired, at the end of a long day, they've made lots of decisions. The last thing they want to do when they come home is to start to worry about what's the track to play next on Spotify. They'd like to just get some music going and start to relax. And this guy here is probably not going to have too successful a night from the look on her face. He's focusing on his mobile device rather than the girl he's with. So the social occasion is also important for how we should be using the technology. And this is part of the general issue of many of you are working on intelligent systems in some form. You're performing inference, machine learning, you're trying to do something that can make decisions. How should that be engaging with the user? Are we trying to replace the user? Are we trying to give them abilities they didn't have before? How are you going to share activity together with the user? So are we having the user as a manager of this system? Are they directly engaging through the system but with extra powers? And if you think about what it feels like when you leave your phone at home in the morning, if by chance you've left your phone in a different jacket, a lot of people describe that as feeling as if part of their brain is gone, because how many of you can still remember 30 phone numbers? 15 years ago, you probably all could. Now, how many do people remember? Maybe 4 or 5 key numbers. How many of you use a GPS system even in your own city to get to places which you might actually travel on fairly frequently? You see lots of people starting to become dependent on the technology. So we could think about designing systems not just to support us, but to teach us how to do something so that we don't need that support in future. So here's an example of something we did with Swansea and Nokia for the younger members of the audience, Nokia used to make mobile phones, so they had an interest in this.
Meet John. He's visiting Rome for the first time. Within the next couple of hours, he would like to find a local restaurant where he can get a good risotto and a glass of wine. John consults his phone, which recommends a place about 1 hour walk from where he is. An arrow on the map points out the direction, and John starts walking. On the way, John is enjoying the city, and he stops to visit some stores and have an espresso. When reaching a junction, he feels uncertain whether to go right or left. Some suspicious-looking people are hanging out down the street, and John feels uncomfortable showing his expensive phone. He sticks the phone in his pocket and starts an in-pocket probe of the surroundings. When the phone is pointing the right way, he gets an affirmative buzz and continues to walk in that direction. When he reaches the restaurant, he feels good about having found his own way. Pedestrian navigation differs from car navigation mainly in the sense that movement is more flexible. This increases the likelihood of detours from the planned route. Audio feedback is often not wanted as it can lead to uncomfortable situations in public, and turn-by-turn commands can be perceived as controlling and non-spontaneous. For a pedestrian, the best would be to avoid having the phone pushing intrusive commands and instead allow the user to be in control by only asking for directions when needed.
So the idea behind that was often we've just taken an interaction method that was designed for one mechanism, so driving in a car, where you have limited attention. It's been carefully designed to just give you the information that you can cope with to make the next turn, and applied that in areas where it just shouldn't be used, like pedestrian navigation, and especially in a context of you being on holiday in a city where you are actually quite happy to be distracted and you want to engage with the city and to learn how to move around that rather than having to spend your life walking around every few yards being told to turn left or right. So it's about who's in control and how you're bootstrapping from some initial cues to have somebody learn how to engage with the city on their own terms. And the system was also dealing with, these are some of the noise distributions on the magnetometers for the phone, showing the difference between having a device sitting on a table, having it in your hand with tremor, and having it in motion while you're walking. So you've got uncertainty in these signals that you need to deal with as well. How do you design to cope with these uncertainties? And the particular system was designed so that if you had the phone level, it would give you vibration feedback when you were pointing in the right direction, but it would not bother you otherwise. So you could choose, whenever you felt confident to move through the city, you could be in control. If you felt a bit like you'd lost your bearings, you could just point towards whatever the waypoint was you were working towards, where your hotel was, where the centre of town was, and that could reassure you that you were going in the right direction. So that's an example of simplifying the interface so that you don't need to have it out all the time. You can engage with it when you want, and you can also learn to take over the parts of the tasks that the system doesn't need to do for you. So this gets us on to the point of how should we engage with intelligent systems. Do we want to have this notion of the phone or the technology you're using as a butler who knows your every whim, who can direct you to do whatever you had planned to do before you thought of it? Or should we think of it more as a horse, where it does some things for you, it can take over some responsibility, but you're still in control, but you have intermittent feedback from the device. So if you think about riding a horse, you've got the horse continuously reading the rider's intentions in terms of pulling on the reins, which direction to go on. It can feedback its state from its gait, from potentially shuddering a bit if you're trying to take it in a direction it doesn't want to go because it feels it's not competent there. There's strengths and weaknesses to both parties. The horse might be scared about a region the rider knows is perfectly safe to go in, but on the other hand, maybe the horse giving some feedback might alert the rider to the fact that this is not such a clever place to be moving towards. And at certain times, the rider will know, I think the horse is going to be a bit unsettled here. I'm going to take more control and tighten up the reins. At other points, the horse is able to be in charge of more of the task, you can loosen the reins and let it go. And I think this notion of tightening and loosening the reins is an interesting one to take into technology and say, how can we build systems that allow you to change the level of engagement easily? So there's been some work at NASA. Flemish et al. Had a paper on the H metaphor, and the H was a mix of horse and haptic in that particular paper, but it was about looking at autopilot systems and pilots engaging together and how you should provide feedback. So in control theory terms, you can think about this as how far in the internal loops should you be working. You could be at a more managerial level in an outer loop giving the general direction. That might be a particular bearing to fly on or an altitude to fly at, or you can be having direct control of the ailerons. The more detailed control you have, the more rapid your responses have to be, the more bits per second you're having to generate to control the system, the more you have to pay attention to the feedback. So you want to be able to potentially move in and out on this depending on how competent you think the autopilot is to solve these problems. So in the riding one, if you've got a rider with executing frequent, certain, deliberate actions, the horse is going to move automatically. If the instructions become more vague, the horse will take over more responsibility, and you could imagine the same to be true in technology. So what we want to look at is how we can let go of the reins in casual interaction. So looking at it from the control theory perspective, you'd say if you've got very accurate and timely control, precise execution of commands, then you've got a high level of engagement or focus. If, however, you've got vague or uncertain input, and that might also be intermittent feedback or vague feedback, then the system can take over some of that control for you, and that's then casual interaction. So you might see a spectrum of these activities where if a system made very gradual changes as the context changed with some change in the environment, or you might have some vague waving near the device, that might be examples of casual interactions with the device. As you move up in the level of engagement, maybe something rings and I just give my device a quick squeeze, then I'm not giving very precise input, and that's fine. I might have multiple fingers patting in a particular pattern. Again, it's a reasonably fast in and out movement, but you're adding the number of bits in that signal, the level of precision required. Or I might be going through very detailed closed loop interaction with a high level of engagement, playing a game, for example, in full screen mode. I need to respond within milliseconds or else I get a poorer score. So that would be the other extreme. So here are some characterizations of these focused interactions: frequent, accurate sampling, low latency responses, extended periods of continuous control, essentially a high channel capacity from the user's outputs to their senses. So they're highly empowered in the system. Casual interaction is whenever you degrade this closed loop behavior. So that might be intermittent interactions, an uneven distribution of interaction over time. So you might have a few seconds of interaction and then ignoring the system. You might have asymmetry in the interaction loop, that you might be very accurate feedback but inaccurate input, or vice versa. So you're in general getting a lower channel capacity from your outputs to your senses, and again that's lower empowerment in the technical sense. So what sorts of examples of this will we have? We think that in the near future devices are going to sense more on the device and around them. We'll be having combinations of sensing at a distance around the device and embedded sensing from Kinect-like sensors in the environment. These are potentially going to give us the ability to have more casual interaction. So we wanted to look at how could we give users the power to choose how much they want to engage. So this is a little study we did to see how users adjusted their engagement when we gave them a few different levels of interaction. So it was done on a desk. Some of you might know Daniel Buschek, who before he came to Helsinki for a while was in Glasgow, but he's now back in Munich. So here there was a sensor here. They were controlling something on the screen, and the task was to take a ball through an obstacle course with hand movements. So there were a number of different levels of difficulty of task where people had to take the ball through, and You could take an index of difficulty like Chai's steering law, which integrates up the inverse path widths over that trajectory, and look at how did people behave for different difficulties of task. So we had 3 different control options which would have different levels of effort. You could actually touch the capacitive array, so that would give you high precision input, and you would be able to move the ball in a detailed fashion. You could hover over the device, so that because we had slightly larger pads, it could sense up to 3 or 4 centimeters away, and so you could move things by hovering over, and that would apply a vector to the target, or you could just wave your hand in a coarse gesture above it, and it would move roughly in the direction that you were waving. So we had the crude gestures being picked up by a Kinect above the device, and the capacitive sensing for the lower levels being done with a shake and an external. This is our own sensor pack and a capacitive sensing board. And as the index of difficulty increases, you see more and more use of the precise inputs. For the easiest levels, people would just use the hover or gesture input, and so you can see a count of the casual gestures being used more when you had less difficult tasks. So it's not a big surprise. People did what we were expecting. They used least effort when it was possible to get away with that. Now, what happens as you start to build in sensing that can sense things around the device, which knows when you're in a particular situation, and that could be a particular room in your house, it could be whether you're at work or at home, or that you're just in a particular city. If we're focusing on touchscreens and personal displays, then you've got your private immersive experience. When we're away from the touchscreen, we can potentially engage less and have less precise input and less precise feedback. So we want to look at this and see, can we use these ideas to engage more mindfully with our devices? And whether making things context aware and adaptive is going to help us in that matter. So it's not just, obviously if you're further away from a device, it's going to have a more crude sensing of your input. Similarly, you could have more basic feedback to the user. So this is not work from our lab, this is from Michael Roh's lab, and it's a paper by Chin et al.
I present to you dynamic ambient lighting for mobile devices. The information a normal mobile device can show is limited to its display. With dynamic ambient lighting, the device has now a new way to show additional information to the user. In this example, an Android application I developed called Public Transportation Locator, the ambient lighting helps the user to locate nearby public transportation stations. Take this blue spot, for example. It represents a subway station in the direction of the light. Purple spots are bus stations, so as there are 2 spots on the left, I know I can expect 2 bus stations there. When I scroll the stations off screen, you can see how the lights start to appear. There's also a purple spot to the right, so there has to be a bus station there too. As the spot still hasn't disappeared, I know I can find another station to the right. You can see the helping effect of the ambient lighting even better when you're zoomed in. Here I try to navigate the bus stations to the left again. As you can see, I do not only know that there are 2 stations to the left, but I can also locate them very precisely. Dynamic ambient lighting is of course not limited to the previously shown usage. This example application called Call Detector demonstrates a way to interact with the light. So here I receive a call. Now if I'm preparing food and my hands are wet or dirty, I don't want to touch the screen. Cleaning my hands would probably take too long, so instead I simply touch the red light to reject the call. If I want to take the call, I can, as you have probably guessed, touch the green light. This will answer the call and turn on the speakerphone, so I can talk freely.
So you're seeing there an example of some basic feedback, but also sensing around the device. And you could also imagine breaking out your displays and having a bunch of little LEDs and low resolution displays associated with pictures of your family members around the house or associated with particular properties. how can we use these sorts of low resolution, low bit rate displays along with sensing at a distance, in the same way that all houses have Wi-Fi embedded? Will we see some sort of Connect-like system that provides you with a general purpose sensing, or will it become more localized sensing around the devices, for the way we have in things like the Nest thermostat, which can sense proximity? But we will have a combination of a range of different sensor types of different resolutions and different bit rates and different display types. How can we build systems that work with these? And one of the metaphors that might well come into that is that the engagement with a particular element of the system drops off with distance. In some cases, that's a natural consequence of the sensing and the feedback. You know, if I'm 10 meters away from my mobile phone, I can maybe see if it's lit up or not, but I can't see anything more specific than that. Similarly, the sensing mechanisms built into it may become poorer at a distance. In other cases, it might not be a necessary consequence of the sensing, but it might be a good metaphor to choose to give people a relationship of, okay, if I'm far away, I'll have less precise control over it. And designing for these different bandwidths is an interesting challenge. Should you be just reducing the field precision for a particular input so that you discretize it in more crude fashions, the more low resolution the input is? Do you combine a number of fields into a single one that gives you fewer degrees of freedom but easier control over it? Or do you have an intelligent agent that takes over responsibility at a certain level and you give it some guidance as to what to achieve while you're not able to use high resolution input? And in terms of design challenges, should we have a continuum of these levels, or should we have a discrete set of levels that we work at? What's going to be easiest for people to cope with and learn how to work with? What sort of interactions are appropriate for any given device? And how can you develop an interaction metaphor that's going to stretch from a hand wave to detailed manipulation of a graphical user interface on the screen? What happens when you lose certain channels? If you're touching the device, you've got vibrotactile feedback. As soon as your hand's away from that, you lose that to some degree. And how can you have fluid switching between these levels? So I'm going to give some examples of systems which take over some responsibility from the user and look at features of that. So the first one I'm working with is Mood Agent, which is a software system you can download for your phone. It generates music playlists for you, but it's nice because it's involving machine learning for perception of complex input, the MP3 files. You can visualize complicated high-dimensional data and have users interacting with that in different ways. It's a nice example of predicting subjective responses to objective data, and it touches on recommender systems, which is always a hot topic. So this is commercially available. There are 20 million users, and it works with 25 million tracks in Spotify. You can download it for free if you want to play with it, and it's been developed by Synthenetic in Denmark, and Glasgow's been collaborating with them over some years in that process. So here's the sort of general pipeline. You get an MP3 file, you use signal processing to pick out low-level features, autoregressive elements, mel frequency, Kepster coefficients, etc. And then you learn a mapping between these low-level features and subjective values, like how tender is this song, is it jazz, is it rock, what tempo is it? So there are some music students who tag a few thousand tracks, and the system then generalizes to all other tracks. So here you can then, once you have this high-dimensional data, you can then choose different ways of projecting that down to lower dimensions that users can work with. I mean, in the initial commercial release, the system had a very simple interface you see here with 5 or 6 sliders depending on which system it was released on, and you would just slide these up and say, I want more aggressive music, or I want more tender music, and it would generate a playlist for you. So you're not having to type in band names, you're not having to think in great detail about what to play. It's taking over some of that responsibility for you. So you can communicate fewer bits per second in order to get a music playlist. And if the system correlates with the way you perceive the music, then you might still get something you're interested in. But what if you wanted to, say you heard something that sounded interesting and you wanted to know, well, how does that relate to other music? What's going on? Then you could potentially use something like this, a 2D map, which projects down this complex data and gives people a space that they can move around in and engage with that content. So the process is you've got some feature extraction, you've got machine learning, using Gaussian process ordinal regression methods, dimensionality reduction to give you something you can work with, and we overlay a second layer of Gaussian processes to give further highlighting of particular classes. So let's see that in action. Okay, so here's a collection of songs. What you're seeing in this mode is the kind of most important colors for different parts of the space, but if I leave that, I can move into a different mode. So let's say I start to explore this area, then what you're seeing now is a coloring of a Gaussian process prior, which is saying how likely it is that songs in this area would be classified as sad songs. And you see that that's actually one of the problems with doing this on a big display is that a lot of the shading disappears. If you want to try it out afterwards, you can see it on the screen here. It looks a bit better. Let's try and get some more colours. Yeah, okay, the colouring's not coming out clearly on the display, but it's showing the distribution of different classes. You can browse around and see nearby songs, and you can generate a playlist, and that then links into Spotify and starts to play the music for you. Okay. So you can inspect the music on the side and browse around, and for each of these values you can see how they vary in the different dimensions that are being revealed to the user at this point. Press pause. Okay. Okay, so I think that's an interesting example of some of the modern challenges for interaction design. You've got something which is using complex signal processing. You've got human experts providing subjective tags for the content. You're using Bayesian non-parametric models to learn relationships there, but these are uncertain mappings. So nothing in here is without uncertainty. And there are things that it's going to have struggle to deal with. So cultural aspects are things which are humour, or things which are going to be quite difficult for it to deal with. They also had to build in an Udo Lindenberg factor because he appeared all over the place and it was causing all sorts of problems. So the Germans are responsible for lots of things in life, and Udo Lindenberg is one of them, and that caused the machine learning a lot of problems. But yeah, so specific cultural issues are things where the system is never going to do a good job, and that's where humans are going to want to come in and be able to bump the system out of that particular mode and push it in the right direction. You can also pull in information from the millions of users using this and get the things which are not easy to do by machine provided by other users if you make it worth their while in some way. So that was a 2D mapping, which was something which would be a very engaging system. You could have simple picks, but you could go down and pick out more detail and look at relationships between the songs. We were doing some work with Bang & Olufsen, the Danish hi-fi manufacturer, and they were keen on having something which was a lower level of effort and also fitted with their design goals. If this video actually opens up, we shall see it. So here we had different interfaces, some using a simple dial to revisit the old-fashioned radio style interaction, but we could combine this with pressure sensing so that if we had a one-dimensional projection of the music space rather than a two-dimensional. That meant you could just either dial or drag the system to a particular point in that 1D space. The system also knew from Last.fm your listening pattern, what songs you listen to frequently. If you didn't apply any pressure, it would just take you roughly to that area and basically draw from the probability of each of the tracks given, conditioned on your previous listening behaviour. If, however, you had something more specific in mind, you could apply pressure to the screen and it would take you into a more focused level and give you more control, more engagement, and you could pick what you wanted. So you've got a single interface that lets you just either swipe or turn to roughly the right point in the music space and then hear whatever it has to offer, which can be conditioned on your previous behaviour, or you apply pressure and have full control and select what you want. So it's another example of how you can move up and down in the level of engagement. And we've also been using this in a music player that was designed for disabled users using an EEG-based brain computer interface. And because entering text to pick the tracks that you wanted was far too much time given the bit rate of these devices, we used the Mood Agent system to allow you to pick from a pie chart of mood generators which would generate a particular type of playlist. But if somebody had a specific desire, they could move into this binary tree that was made to look like a record collection, and the alphabet was basically spread out in a series of binary choices, and you could pick the track that you wanted from that. So again, giving you an easy option if you were prepared to pick something quickly, and if you had the energy to do something more detailed, you could go into that in more detail. So another example of using pressure to exert your will is we've been looking at learning touch models. So when you touch a mobile phone, what is it you're actually touching? You know, you've got your finger is much larger than the targets you're trying to hit. So everybody has a personal model of what they're trying to achieve, which they then get trained by their phone to change. And we've been using Gaussian process powers to learn offset models for individual users and for particular devices. But you've also got a language model that's bringing some language-specific features in there. And actually, I'll just move to the video because that shows things. So you can have a model that's predicting the offset, and you have another one that's saying how likely different letters are conditioned on what you've entered so far. And here's a
text input on modern touchscreen devices is an inherently inaccurate task. In this paper, we present a novel decoder which combines probabilities from a user-specific touch model and a statistical language model to correct for input errors. We explicitly incorporate uncertainty when searching for the most likely word given a series of touches, and show that this significantly improves the quality of our corrections. In a further study, we allow users to provide certainty keys to the system and dynamically control how autocorrection is applied.
So the system has the ability to sense what it thinks you're trying to do, but as you all know, if you've used a poor language model, so for example, if you have a Glaswegian dialect and you want to write some words in Scots, the iPhone or Android tends not to have that as a feature. So you're writing this text, you know that the automated system is not going to help you, it's actually going to make things worse. So what we did was we allowed you to add pressure so that if you pushed hard, the system would believe you. If you didn't push hard, it would use its intelligence and put a best guess in. So there was a simple prototype using a pressure-sensitive input, and when people felt that they were writing a word that they didn't expect the system to know, they could just push harder. So that's tightening the reins, and the system had fewer corrections and was faster when people used that. So that's a nice simple example of being able to work on that. So if we are working on things with a more casual fashion, you'd expect there to be a lower bit rate in communication at that level. So one of the things that we've been looking at is, for a given person and a given sensor system, how can you measure how much they can communicate with that particular system? So we want to look at the variety of gestures that can be interpreted, and we've got a whole range of possible sensor systems that could be used for these things. How do you compare what people can achieve with these? So we want to look at the channel capacity. What's the bandwidth? How does that bring in the signal and noise? So we've got the variability relating to the bandwidth. We've got the reliability associated with how repeatable these gestures are. And you can compare a number of different systems. You might have a system with low variability, so you can generate few things, but you can do that fairly reliably. You might have a system with high variability. You can express lots of different gestures, and again, you can do that reliably. Or you might have that same level of complexity, but people might not be able to generate these particularly reliably. So you've got this number of possible movements a user could achieve, or the combination of user and sensor system. There are other aspects which are important, things like transmissibility, so how quickly and easily the skills required to interact with the system can be learned, and that's going to be affected by feedback from the system, and how you can learn movements watching other people. And recognizability is how effectively your software can classify these sensor sequences into classes that link to user intention. So this particular aspect is about measuring the repertoire, the number of measurable and performable movements for a given joint user sensor system. And it's breaking things down into a bunch of primitives, having a running window, and then looking at that. And a sensor system is built that could take the raw data, take windows, smooth it, look at parameterization of that, and then add new elements essentially to a code book, and you could have a self-organizing map that could grow and link different parts of the video sequence for these two parts of that space. So designers could potentially look at these and gain some understanding to what things people learned quickly. But it's easier to see the video rather than hear me talking about it.
There are many ways to swing about an arm. When designing interactions with novel input mechanisms, it would be useful to quantify, categorize, and analyze the space of all feasible and measurable movements. Our approach to solving this problem is much the same as the way a dolphin would be trained to perform tricks. Dolphins, naturally rather recalcitrant, can be effectively trained by positive reinforcement. By rewarding originality rather than conformity, the space of possible behaviors can be explored. We built a system using a small inertial sensor which can be attached to various body parts, and we developed an algorithm which rewards originality using sensible metrics. Users receive audio feedback which indicates that their movements are different from ones they have performed before. Eventually, users run out of motions to perform. We constructed a suite of tools to analyze the captured motions. We formed a low-dimensional projection of the motion features to construct a two-dimensional map. Movements can be cross-referenced against videos and sensor traces.
Okay, so that lets you explore how different members of a population could access it. So how do older people work with it? What happens if you've got something in you've got a shopping bag in your hand? What happens if you're in a particular social context? So if you ran this experiment, the movements people would be prepared to make in their own office would be quite different from what they would be prepared to make in a restaurant or in the underground. And it lets you look at the sorts of interactions that you can perform with a given system and say, well, there are some which are everyday actions, so you probably don't want to use them because they'll be misinterpreted as gestures when they were just everyday motions. There are things which are unlikely to be done, so they might not be easy to discover. There are good gestures which are not that common but easy to generate and easy to learn. Others which are socially unacceptable, they're too embarrassing. And others which you can do but are painful or bad to do in a repeated fashion. Another, I'm going slightly over, but I'll just push through this. Another thing you can do is you can use the environment around you to constrain things. So you might have, it might be more socially appropriate to move around, even if you could achieve that action directly on your touch screen. Sometimes restricting the ability of a device, forcing people to do something in their environment might be a more socially relevant or acceptable task. So if you're talking to somebody, going over and switching off a TV is maybe better than sort of looking at your mobile device and doing something on that, especially if there's a chance you'll be captivated by the device and start to interact with other things. So here's just a little...
Mobile devices weave themselves into the fabric of everyday life, whether we're making a cup of tea, watching the television, or heading out the door. However, we still suffer when it comes to navigating crowded displays, operating small keyboards, or waiting for content to load. With a little help from the structure of the environment, we can improve mobile interfaces and bridge the gap between digital and physical worlds. With the Microsoft Kinect, we can simulate indoor positioning and prototype new interactions for mobile devices that react to the structure of the room. Users can associate their digital information with artifacts of the environment and use their knowledge of the space to navigate the interface of their device. By prototyping mobile interactions in spatial environments, we hope to better support future mobile users, wherever they are.
So sometimes making your actions visible to other people is going to be more appropriate. If somebody wants to explore your book collection, at the moment they'd have to take a picture on your ebook collection. They'd have to pick up your Kindle, and that's your device, and they'd have to browse it. Whereas if you could combine a sort of peephole AR-like display with the Kinect, so that somebody could put their book collection up on the wall in their room, then you could have a normal, socially acceptable thing of, oh, what have you been reading recently? And you could browse through somebody else's book collection. And it might be more acceptable to do that physically and then be able to comment about it than have people sort of slotted into their own devices. So you might, to have more mindful interaction with your devices, you might want to make your actions visible to other people. That encourages you to think about the other people in the room, and they think about what you're doing, and that can trigger other rich interactions around what you're doing on the device. So we've been doing things like putting in Bluetooth devices in different rooms to do very quick and dirty localization and seeing what applications do people run in these spaces. If you can predict their needs, so we had a system that could look at what apps you started in which locations. So you could break it down between living room, office, car, kitchen, and that means you could choose to make those apps easily. So we had a system where you could make them easily accessible when you're in that space, which might mean that you can do them quickly, but you don't start to do other things. And you might, through some shared decisions with the user, say, do you want to inhibit things? So if you realize you keep on falling into Facebooking in the evening on the sofa, you could choose to eliminate that as a feature, so the system could either make it very difficult to get to or impossible, depending on what you want to agree with your mobile device. So, summing up, I think if we can get our devices sensing more of the activity around them, giving us a different set of levels at which we can interact with them, and we think about how we can work that into a social context, then we're going to potentially be able to cope better with the attractiveness of all the things that we're building at the moment. And if you want to try and work on some of these, we have internship opportunities in Glasgow. So, thank you. Questions?
So you were talking about the future devices sensing quite a lot, and that is pretty obvious. They are doing it already, so to a certain extent. But what about devices that would act with us and help us with our force? This kind of physical action aspect where you are using mirror neurons to figure out what the device is doing, and it does this vice versa.
Right. So are you? Let's see. I think.
So, for example, a machine that carries our bags.
Yeah. Okay, so an awful lot of the early work in this area was in more classical teleoperation or robotics work. So a lot of the man-machine systems work would have been in things where you were directly controlling something that had mass dynamics and dangerous consequences if things went wrong. I think it's interesting, and for example, we put in a Horizon 2020 bid for a proposal where we want to combine some of these ideas for work with people who've got spinal cord injuries, and we're sticking on a sleeve of functional stimulation for the muscles in the arm. And if you want somebody to be able to pick up a cup, then they can generate that intention, but it might be a pretty low bit rate sensor, so it might be a shoulder joystick, it could be a brain-computer interface. The system is now going to start to try and generate that trajectory, but maybe there are two candidates. The system might couple in a Kinect or other camera and a projector to say, right, we can support you doing this, but which of these targets are you going for? And you might have some way of guiding it towards one or the other. And then as it gets closer, there could be an RFID tag stuck to the cup which tells the system what's the ideal grasp to generate for that. So that would be an example of something where you could bring some of these elements together.
I was rather thinking about the fact that it actually, do you think that this kind of basic interaction, kind of modalities and ways that you showed us would be different? Or does one now need to have different ways of interacting with the devices than the ones you already described? So how applicable this would be on those?
So I'm trying to just sort of home in on a specific example. So are you imagining, let's say we had an intelligent suitcase which could follow after you or something, and then you might have gesture to say, come on, up, stay close, or you know that this is a dangerous part of Helsinki, and don't stay too far behind. They're dangerous around here. So you bring the device closer to you or something. Is that?
For example,
yeah. So I mean, I think anything where you're closing the loop. So there are always going to be questions. What feedback do you get from the system? So in that case, how could the suitcase express its state and its uncertainty about your intentions? So the idea is that rather than the designer solving all the problems in advance, you allow the system in real time to share the load where it's trying to infer what you're trying to get at. It can display its state somehow. That might be by jiggling around, or it might be by having LEDs come on. And you can respond to that, and that changes its inference about your intention. So that you can have a very general representation of it, but for any specific case, you're going to need to create a metaphor that people get. And that's often where the real challenge is finding. So the Wii, for example, has really lousy algorithms in terms of interpreting what's going on, but by creating a story, by saying you're playing tennis, and you do something with your arm that is tennis-like because you understand what tennis is about, and it plays tennis. But if you've ever boxed on a Wii with a 5-year-old, and you're slugging away like this, the 5-year-olds usually worked out that all they have to do is this, and they beat the hell out of you. And as soon as you've experienced that, the metaphor's gone, you just don't really believe in the system anymore, and it's harder to get engaged with that task. So picking the metaphor can really make it much more natural to engage with. How you get that to work for a specific system will be very dependent on the form of that system and the places you're going to use it. Okay, Tim?
Yeah, so I'm not exactly sure if I can formulate a question, but I just wanted to hear your comment on something that I think I just realized listening to your talk. So as a machine learning researcher, I was always thinking that For instance, a predictive text input has always been extremely annoying, and everyone hates the auto-correct feature because they make these mistakes, and then you get annoyed and you switch them off. So I always thought that it's the task of the machine learning researcher to make them so good that they don't actually make these mistakes. But I think now that what you showed said that that's not maybe the only way to make them more useful. Like, for instance, this pressure input thing could help, so that even if the model is not so good, even if we haven't reached perfection in terms of machine learning, we can make them applicable and useful.
You've got two approaches. One is that you assume that the design team creating this product have godlike abilities or finances or time to really make something that solves all the problems. Now the problem is we have a very heterogeneous user base, so everybody is slightly different, and many of the user categories are not worth spending the money on. So, and you see that now, I guess there was a very different attitude within, say, Nokia to meeting the needs of the world than there is in Apple, which is kind of designing for 30-something Californians. And so different cultures and companies will look at different levels of diversity. And you can take it to an extreme, but at some point you're not going to be aligned with the designer. And that comes faster or slower in different applications. And any system that has any level of intelligence in there, if it's going to be successful, either it's a really simple problem, or it has been worked on enough to simplify it, or you've constrained the user's variability to make it simple. So by changing the shape of the device or the format, you've eliminated lots of the things that people would normally have done otherwise. So you can constrain the user's expectations or ability, or you can give them a metaphor which naturally constrains their actions. Or you give them a mechanism for bumping the system out of whatever it was going to do and letting you easily take control. And you can see, for example, I don't know if people have used the shape writer or swipe or gesture entry on Android devices, but that has now become a really nice system. So this is a system where you can just tap on the normal keyboard if you want to, but you can also drag the finger around the letters of the word you're going to enter, and that performs a gesture, and that can be a much higher bandwidth way of entering text, and it's using a combination of the gesture recognition, but you've got a framework of the standard keyboard that people are used to, and if for any reason the gesture's getting too complicated or they've forgotten exactly how the system works, they can revert to using it as a normal keyboard. So it's giving you a framework to learn the gestures. Sometimes you'll be able to do these without actually looking at where the keys are as you develop your skills. But if you haven't used the system for a while, you can always re-enter it and just plod away tapping keys. So I think that's a really nice example of a scaffolding that lets you learn a different way of engaging with it, but you can always drop back to simple, old-fashioned, very specific cases, and in our case, adding pressure if you then want to avoid it using its intelligence in the model because you know you'll get it wrong. So yeah, I think we agree.
You were talking quite a lot about this level of engagement, affecting the way the system should work. But if we turn this around, that we actually want to manipulate the engagement. I give a simple example. You have some e-learning application and you want the kids to get more engaged, like putting their attention to it with some gamification or whatever. I would just like to hear your comments about what you think about the limitations to this, because I think we cannot manipulate the level of engagement ad infinitum.
Okay, but tell it to your friends who've gone to work at Rovio, whose entire job is to try and control your behaviour, to get you to start playing this game and not to shake it off. Right. So lots of companies, I'm trying to say, well, actually, we want ways of freeing people up, but many people. So I don't know if any of you know Sami Ronkainen, but I was having a chat with him on Wednesday morning. He's now at Rovio, and he's saying, well, I was pitching some of this stuff, and he's saying, well, our job is to do the opposite. We want to get people addicted and get them spending all their time on this. And there's the question of then at what point do you see the way television has lost because of that, because TV thought that it had a lock on people's attention, and now the kids have just walked away from it and are just not engaging with it. And at some point we'll maybe see similar things happening with games. But yes, so if you think about these control loops, you've got the human thinking that they're controlling the device, but the causal flow, and that's an interesting question. So here, so here I've been sort of imagining an agent is human A putting its inputs into this environment, controlling stuff. But this environment might well have a number of other actors who could be human, and they're controlling you, and you're controlling them. There's an interaction there. There's an ebb and flow of who is actually driving the causal flow. But many games manufacturers are going through your phone, and they're desperately trying to keep you engaged for as many minutes of the day as possible to sell you whatever services they're doing, or have more of a likelihood of you buying an in-game purchase or whatever. And so it might be interesting if you could start to use some of the causality measures that people have been working on in brain research, in machine learning, in economics, and start to give people some feedback. By the way, to me it looks like you're being controlled by them and not vice versa. How can we allow people to start to build in protective layers that they can get some nudges and prompts to say, well, you're responding in a very responsive manner to every time a new story comes up on Facebook. You're being driven by that rather than you pulling information out. So this push-pull relationship in apps, are users pulling information out? Are they putting energy in and getting information out? Or are they being driven by the system? And so picking up the causality of these loops is quite an interesting challenge.
Let's take one more question from you.
Yeah, I was thinking that have you considered voice, because I've been quite happy using, for example, Siri nowadays. For example, when I'm cooking in the kitchen, set the timer for 10 minutes. That's really casual interaction for me. But then also there's the possibility of you use the ambient sounds to determine what I'm doing. It would be probably quite easy to pick up that I'm in the kitchen now cooking, or if I'm jogging or at the gym lifting weights.
Yeah, so I think any inference from the vibrations, the sounds around you is something which can be useful for the system. Having a Glaswegian accent means that Siri is fairly useless for me, but again, it's about how much have you customized the system for different people. It was amusing for my son for a while. We could all have goes at trying to get it to do things, but I know nobody in Glasgow who uses Siri for anything other than entertainment.